In the vast expanse of space, approximately 4.5 billion years ago, something extraordinary began to unfold in what would become our corner of the universe. A gentle, swirling cloud of gas and dust, known as a nebula, began its slow and majestic dance of creation. This was not a violent birth, but rather a gradual, peaceful gathering of cosmic materials that would eventually form the solar system we call home today. The story of our solar system begins with this primordial nebulous, a vast collection of hydrogen, helium, and heavier elements that had been forged in the hearts of ancient stars. Picture this cloud, if you will, as a soft, luminous mist stretching across distances so vast that light itself would take years to cross from one edge to another. Within this gentle cosmic fog, tiny particles of dust and ice floated serenely, each grain carrying within it the potential for worlds yet to be born. As eons passed in the quiet darkness of space, something began to disturb the perfect stillness of this nebula. Perhaps it was the distant shock wave from an exploding star, or maybe the gravitational whisper of a passing stellar neighbor. Whatever the cause, this gentle disturbance set in motion a process that would take millions of years to complete, a slow and patient transformation that demonstrates the universe's capacity for both power and grace. The nebula began to contract, not rapidly or violently, but with the measured patience of cosmic time. As it contracted, it began to spin, slowly at first, like a figure skater beginning a gentle pirouette. This rotation caused the cloud to flatten into a disk, with most of the material gradually settling toward the center. At the heart of this growing disk, temperatures began to rise as gravitational forces compressed the gas and dust into an increasingly dense core. During this early period, the disk surrounding the protosun was a place of remarkable activity. Tiny grains of dust began to stick together when they collided, forming larger and larger aggregates. These early building blocks of planets grew through a process called accretion, a gentle gathering of materials that would continue for millions of years. The disk itself was not uniform, but contained regions of different temperatures and compositions, which would ultimately determine the nature of the planets that would form in each zone. In the inner regions of the disk, closest to the forming sun, temperatures were high enough to prevent the condensation of water and other volatile compounds. Here, only rocky materials and metals could survive in solid form. These materials would eventually come together to form the terrestrial planets, Mercury, Venus, Earth, and Mars. Each of these worlds would develop its own unique character, shaped by its position in the disk and the materials available for its formation. Further out from the center, beyond what astronomers call the frost line, temperatures were cool enough for water to freeze into ice. In these outer regions, the building blocks of planets could include not only rock and metal, but also vast quantities of ice and frozen gases. This abundance of material would allow for the formation of much larger worlds, the gas giants that we know today as Jupiter, Saturn, Uranus, and Neptune. The process of planetary formation was not a chaotic collision of cosmic debris, but rather a gradual and methodical assembly. Small particles clumped together to form larger bodies called planetesimals, which were roughly the size of asteroids. These planetesimals then continued to grow through gentle collisions and gravitational attraction, eventually becoming the planets we observe today. As the central mass of the nebula continued to grow and heat up, nuclear fusion finally ignited in its core, and our sun was born. This moment marked the beginning of a new phase in our solar system's development. The newly born star began to emit a powerful solar wind, a stream of charged particles that swept through the surrounding disk, clearing away much of the remaining gas and dust. The early solar system was a place of both violence and beauty. While the planets were still forming, they experienced a period known as the Late Heavy Bombardment, when asteroids and comets frequently collided with the growing worlds. Yet even this seemingly chaotic time was part of a larger pattern of cosmic evolution, a necessary phase in the development of the stable planetary system we know today. During these formative years, each planet began to develop its own distinctive characteristics. Mercury, closest to the Sun, became a world of extremes, with scorching days and freezing nights. Venus developed a thick atmosphere that trapped heat, creating a greenhouse effect that made its surface hotter than Mercury's, despite being farther from the Sun. Earth, blessed with the perfect distance from the Sun and the right mix of materials, began to develop the conditions that would eventually support life. Mars, the fourth planet from the Sun, started as a world with a thicker atmosphere and possibly flowing water on its surface. The outer planets, Jupiter and Saturn, became massive gas giants, their powerful gravitational fields serving as cosmic shepherds, protecting the inner planets from many potential asteroid and comet impacts. Uranus and Neptune, the ice giants of the outer solar system, formed in the cold, distant regions where exotic ices could condense and contribute to their growth. The formation of our solar system was not an isolated event, but part of a larger story of cosmic evolution. The materials that formed our sun and planets were themselves the products of previous generations of stars, stellar furnaces that had forged the heavier elements necessary for rocky planets and ultimately for life itself. In this way, our solar system represents both a new beginning and a continuation of processes that have been ongoing for billions of years. As we consider this remarkable story of cosmic birth and development, we can find in it a profound sense of connection to the universe around us. The atoms in our bodies were forged in the hearts of ancient stars, and the planet we call home formed through the same gentle processes that created all the worlds in our solar system. This knowledge brings with it a sense of belonging, a recognition that we are not separate from the cosmos, but rather an integral part of its ongoing story. The early history of our solar system reminds us that even the most dramatic transformations can unfold gradually with patience and persistence. The same forces that shaped our cosmic neighborhood continue to operate today, though on timescales that dwarf human experience. Understanding this deep history provides us with perspective on our place in the universe and invites us to contemplate the remarkable journey that has brought us to this moment in time. At the very center of our solar system lies a star that has been our constant companion for over 4 billion years. The Sun, our nearest star, is far more than simply a source of light and heat. It is a massive nuclear furnace, a sphere of plasma held together by its own gravity, where the fundamental forces of nature work in perfect harmony to sustain life throughout our cosmic neighborhood. To truly appreciate the magnificence of our Sun, we must first understand its sheer scale. With a diameter of approximately 1.4 million kilometers, the Sun is so large that over 1 million Earths could fit within its volume. Yet, despite this enormous size, the Sun is classified as a relatively modest star, neither particularly large nor small compared to the billions of other stars scattered throughout our galaxy. This humble status makes our Sun's role in sustaining life all the more remarkable. The Sun's surface, known as the photosphere, maintains a temperature of about 5,500 degrees Celsius. This might seem extraordinarily hot, but it pales in comparison to the temperatures found at the Sun's core, where nuclear fusion reactions occur at temperatures exceeding 15 million degrees Celsius. At these extreme temperatures, and under immense pressure, hydrogen atoms are fused together to form helium, releasing tremendous amounts of energy in the process. This nuclear fusion process is the source of all the energy that powers our solar system. Every second, the Sun converts approximately 600 million tons of hydrogen into helium, with a small fraction of this mass being converted directly into energy according to Einstein's famous equation, E or mc2. The energy produced in the Sun's core begins a journey that will take hundreds of thousands of years to reach the surface, as photons of light are repeatedly absorbed and re-emitted by the dense plasma that fills the Sun's interior. The Sun's structure is elegantly layered, each zone serving a specific function in the star's operation. At the very center lies the core, where nuclear fusion reactions provide the energy that has sustained our star for billions of years. Surrounding the core is the radiative zone, a region where energy slowly makes its way outward through the dense stellar material. Above this lies the convection zone, where hot plasma rises toward the surface, while cooler material sinks back toward the interior, creating massive circulation patterns that help transport energy to the photosphere. Above the visible surface of the Sun lies the chromosphere, a thin layer of the solar atmosphere that glows with a reddish hue during solar eclipses. Beyond this is the corona, the Sun's outermost atmospheric layer, which extends millions of kilometers into space and maintains temperatures of over 1 million degrees Celsius. The corona is the source of the solar wind, a continuous stream of charged particles that flows throughout the solar system, creating the space weather that affects all the planets in our cosmic neighborhood. The Sun's magnetic field plays a crucial role in shaping its behavior and appearance. This magnetic field is generated by the movement of charged particles within the Sun's interior, creating complex patterns that extend far beyond the star's visible surface. Sunspots, those dark patches that occasionally appear on the Sun's face, are regions where the magnetic field is particularly strong, temporarily cooling the surface and creating areas that appear darker than their surroundings. Solar flares and coronal mass ejections are dramatic manifestations of the sun's magnetic activity. These events release enormous amounts of energy and particles into space, sometimes affecting Earth's magnetic field and creating the beautiful auroras that dance across our planet's polar skies. While these phenomena can occasionally disrupt communications and electrical systems on Earth, they also serve as reminders of the dynamic nature of our star and its ongoing influence throughout the solar system. The Sun follows an 11-year cycle of magnetic activity, during which the number of sunspots and solar flares waxes and wanes in a predictable pattern. This solar cycle affects the entire solar system, influencing everything from the density of the solar wind to the frequency of auroral displays on planets with magnetic fields. Understanding this cycle helps us appreciate the sun not as a static object, but as a dynamic, ever changing star that continues to evolve over cosmic time. From Earth's perspective, the sun appears to move across our sky in a predictable pattern that has served as the basis for human timekeeping throughout history. This apparent motion is, of course, due to Earth's rotation on its axis and its orbital motion around the sun. The changing seasons that we experience are the result of Earth's tilted axis, which causes different parts of our planet to receive varying amounts of solar energy throughout the year. The sun's influence extends far beyond the provision of light and heat. Solar radiation drives Earth's weather patterns, from the gentle breezes that cool us on warm days to the massive storm systems that bring rain to nourish our crops. The sun's energy powers the water cycle, lifting moisture from the oceans and transporting it across continents as clouds. Photosynthesis, the process by which plants convert sunlight into chemical energy, forms the foundation of nearly all life on Earth. Even the fossil fuels that have powered human civilization for the past few centuries are ultimately solar energy stored in ancient organic matter. Coal, oil, and natural gas all represent sunlight that was captured by plants and other organisms millions of years ago, concentrated and preserved in the Earth's crust. In this way, the sun has been humanity's primary energy source throughout our species' existence, even when we were not fully aware of this connection. The sun's gravitational influence extends throughout the solar system, holding all the planets in their orbits and maintaining the delicate balance that has allowed our cosmic neighborhood to remain stable for billions of years. This gravitational force decreases with distance according to the inverse square law, which explains why the inner planets orbit much more quickly than the outer planets. Mercury, closest to the Sun, completes its orbit in just 88 Earth days, while Neptune, at the edge of our solar system, takes 165 Earth years to complete a single orbit. As we contemplate the Sun's role in our solar system, we are reminded of the remarkable coincidences that have made life on Earth possible. Our planet orbits at just the right distance from the Sun to maintain liquid water on its surface, a zone that astronomers call the habitable zone, or sometimes the Goldilocks zone. Too close to the Sun, and water would boil away into space. Too far away, and our planet would be a frozen wasteland. Earth's position in this habitable zone has allowed for the development of the complex chemistry that underlies all known life. The sun will continue to shine for approximately another 5 billion years. gradually growing brighter and hotter as it ages. Eventually, our star will exhaust the hydrogen fuel in its core and begin to evolve into a red giant star, expanding to many times its current size. This distant future transformation will mark the end of the Sun's main sequence lifetime and will dramatically alter conditions throughout the solar system. However, these changes are so far in the future that they seem almost inconceivably distant from our current perspective. For now, we can take comfort in the sun's steady, reliable presence in our sky. Day after day, year after year, our star continues its ancient nuclear dance, converting hydrogen into helium and bathing our solar system in the life giving energy that makes our existence possible. As we prepare for rest, we can reflect on our connection to this magnificent star and the countless ways it has shaped our world and our lives. In the inner reaches of our solar system, where the sun's influence is strongest and most immediate, we find Mercury, the smallest and innermost of the classical planets, named after the Roman messenger, god known for his speed. Mercury indeed races around the sun faster than any other planet, completing its orbit in just 88 Earth days. Yet, despite this apparent haste, Mercury holds many secrets that reveal themselves only to patient observation, secrets that speak to the gentle complexity underlying even the most extreme environments in our solar system. Mercury's proximity to the Sun creates conditions unlike anywhere else in our cosmic neighborhood. During its day, which lasts 59 Earth days, surface temperatures can reach 427 degrees Celsius, hot enough to melt lead. Yet Mercury's nights, which also last 59 Earth days due to the planet's slow rotation, see temperatures plummet to minus 173 degrees Celsius. This extreme temperature variation, the greatest of any planet in our solar system, creates a world of stark contrasts that nonetheless maintains its own unique beauty and scientific fascination. The planet's surface is heavily cratered, bearing the scars of billions of years of impacts from asteroids and comets. These craters serve as a record of the early solar system's history, preserving evidence of the late heavy bombardment that occurred roughly 4 billion years ago. Unlike Earth, where erosion and geological activity constantly reshape the surface, Mercury's thin atmosphere and low geological activity have allowed these ancient scars to remain largely unchanged, creating a natural museum of cosmic history. Among Mercury's most distinctive features are its lobate scarps, long, curved cliffs that can stretch for hundreds of kilometers across the planet's surface. These scarps formed as Mercury cooled and contracted over billions of years, causing the planet's crust to wrinkle and fold like the skin of a drying apple. The largest of these scarps can rise over a kilometer high and represent some of the most dramatic topographical features on any terrestrial planet. Mercury's composition tells a story of formation in the hottest regions of the early solar system. The planet consists of an unusually large iron core surrounded by a thin silicate mantle and crust. This iron core makes up approximately 75% of Mercury's radius, a much larger proportion than found in any other terrestrial planet. Scientists believe this unusual composition may result from Mercury's formation in the high temperature environment close to the young sun, where only the most refractory materials could condense into solid form. Despite its small size, Mercury possesses a magnetic field, though it is much weaker than Earth's. This magnetic field suggests that the planet's iron core is at least partially molten, generating electrical currents that create the magnetic field through a process similar to that which operates in Earth's core. The presence of this magnetic field was one of the surprises discovered by the Mariner 10 spacecraft in the 1970s, challenging earlier assumptions about the planet's internal structure. The discovery of water ice in Mercury's polar regions represents one of the most intriguing findings about this seemingly inhospitable world. In permanently shadowed craters at Mercury's poles, where the sun's rays never reach, temperatures remain cold enough for water ice to persist indefinitely. Radar observations from Earth and measurements by the Messenger spacecraft have confirmed the presence of these ice deposits, suggesting that Mercury may harbor more water than previously thought possible. Mercury's thin atmosphere, or exosphere, consists primarily of oxygen, sodium, hydrogen, helium, and potassium. This tenuous atmosphere is constantly being replenished by the solar wind and by particles knocked off the planet's surface by micrometeorite impacts. The sodium in Mercury's atmosphere creates a faint yellow glow that can be detected by sensitive instruments on Earth, providing astronomers with valuable information about the planet's surface composition and the processes occurring in its exosphere. The planet's orbital characteristics reveal the profound influence of the Sun's gravity on objects in the inner solar system. Mercury's orbit is highly elliptical, meaning the planet's distance from the Sun varies significantly during its 88-day year. At its closest approach, called perihelion, Mercury is about 46 million kilometers from the Sun. At its farthest point, called aphelion, this distance increases to about 70 million kilometers. This elliptical orbit contributes to the extreme temperature variations experienced on the planet's surface. Mercury's slow rotation relative to its orbital period creates a unique relationship between the planet's day and year. While Mercury completes one orbit around the Sun in 88 Earth days, it takes 176 Earth days for the Sun to return to the same position in Mercury's sky. This means that a single day on Mercury, from one sunrise to the next, lasts exactly 2 Mercury years. This unusual relationship between rotation and orbital period results from tidal forces exerted by the Sun, which have gradually slowed Mercury's rotation over billions of years. The study of Mercury has provided crucial insights into the formation and evolution of terrestrial planets. Its extreme conditions test our understanding of planetary processes and help us appreciate the delicate balance of conditions that make Earth habitable. Mercury's lack of a substantial atmosphere, its extreme temperature variations, and its heavily cratered surface remind us of the hostile environment that exists in much of our solar system and highlight the remarkable nature of our own planet's more temperate conditions. Observations of Mercury from Earth are challenging due to the planet's proximity to the Sun. Mercury never appears more than 28 degrees away from the Sun in our sky, making it visible only during brief periods just after sunset. or just before sunrise. These observation windows, combined with Mercury's small size and the distorting effects of Earth's atmosphere, made detailed study of the planet difficult until the advent of space based telescopes and planetary spacecraft. The Messenger mission, which orbited Mercury from 2011 to 2015, revolutionized our understanding of this small world. The spacecraft revealed Mercury's complex geological history, discovered its magnetic field's unusual structure, and confirmed the presence of water ice at the planet's poles. Messenger's observations showed that Mercury is far more geologically active than previously thought, with evidence of past volcanic activity and ongoing surface processes. Mercury's surface features tell stories of a world shaped by both internal and external forces. The Caloris Basin, one of the largest impact craters in the solar system, stretches 1,550 kilometers across Mercury's surface. This enormous crater, formed by the impact of a large asteroid or comet billions of years ago, demonstrates the violent history of the early solar system. The impact that created Caloris Basin was so powerful that it sent seismic waves completely around the planet, creating a region of jumbled, hilly terrain on the opposite side of Mercury called the Weird Terrain. Despite its harsh environment, Mercury continues to reveal new wonders to scientists and astronomers. The planet's extreme conditions provide a natural laboratory for studying the physics of planetary formation, the behavior of materials under extreme temperatures, and the evolution of small rocky worlds. Each new discovery about Mercury adds to our understanding of the solar system's history and the processes that shaped all the terrestrial planets. As we consider Mercury's role in our solar system, we can appreciate how this small, seemingly hostile world contributes to the overall harmony and stability of our cosmic neighborhood. Mercury's rapid orbit and its gravitational interactions with other planets play a role in the long term stability of the inner solar system. The planet serves as a reminder that even in extreme environments, natural processes continue to operate, creating beauty and complexity that reward careful study and contemplation. In the quiet moments before sleep, we can imagine Mercury in its eternal dance around the sun, experiencing its long days and nights, its extreme temperatures, and ancient landscapes. This small world, racing through space at tremendous speed, reminds us that our solar system is a place of constant motion and change, where each world tells its own unique story of formation, evolution, and endurance. Beyond Mercury's orbit, in the growing warmth of the early morning or evening sky, shines Venus, the planet that has captivated human imagination for millennia. Known as both the morning star and the evening star to ancient civilizations, Venus appears as the brightest object in our sky after the sun and moon. This brilliant world, nearly identical to Earth in size and mass, hides beneath its gleaming clouds one of the most extreme and fascinating environments in our solar system. Venus orbits the Sun at a distance of approximately 108 million kilometers, placing it well within what might be considered the habitable zone, if not for the planet's extraordinary atmospheric conditions. The journey of sunlight to Venus takes about 6 minutes, and when it arrives, it encounters a world wrapped in mystery. The planet's surface is completely hidden beneath a thick blanket of clouds composed primarily of sulfuric acid droplets suspended in an atmosphere of carbon dioxide. The atmosphere of Venus is a masterpiece of atmospheric physics, though one that demonstrates the dramatic consequences of a runaway greenhouse effect. The atmospheric pressure at Venus's surface is approximately 92 times greater than Earth's, equivalent to the pressure experienced nearly a kilometer beneath Earth's oceans. This dense atmosphere is composed of 96% carbon dioxide, with small amounts of nitrogen and trace gases, including sulfur dioxide, water vapor, and argon. The greenhouse effect on Venus operates with such efficiency that the planet's surface temperature reaches 464 degrees Celsius, making it the hottest planet in our solar system, despite being farther from the Sun than Mercury. This extreme heat is distributed remarkably evenly across the planet's surface, with temperatures varying by only a few degrees between the equator and the poles, and between day and night. The dense atmosphere acts like a thermal blanket, effectively trapping and redistributing heat around the entire planet. Venus rotates on its axis in a direction opposite to most other planets in our solar system, a phenomenon known as retrograde rotation. A single day on Venus lasts 243 Earth days, making it longer than Venus's year, which is only 225 Earth days. This slow backward rotation means that on Venus, the sun rises in the west and sets in the east, taking approximately 117 Earth days to cross the sky from horizon to horizon. The surface of Venus, revealed through radar mapping by spacecraft such as Magellan, displays a landscape of remarkable geological complexity. Vast plains of solidified lava cover about 80% of the planet's surface, punctuated by thousands of volcanic features ranging from small shield volcanoes to enormous volcanic structures unlike anything found on Earth. The planet's surface is relatively young in geological terms, with most features appearing to be less than 800 million years old, suggesting that Venus underwent a period of global volcanic resurfacing in its recent past. Among Venus's most distinctive surface features are its coronae, circular structures that can span hundreds of kilometers and are thought to be the result of upwelling plumes of hot material from the planet's interior. These coronae are surrounded by complex patterns of ridges and valleys, creating intricate geological formations that speak to the dynamic processes operating beneath Venus's surface. The planet also hosts numerous impact craters, though far fewer than Mercury or Mars due to the protective effect of its dense atmosphere, which burns up smaller incoming objects before they can reach the surface. The highland regions of Venus, known as terrae, rise several kilometers above the surrounding plains and cover about 8% of the planet's surface. The largest of these highland regions, Ishtar Terra, is roughly the size of Australia and includes Maxwell Montes, the highest mountain on Venus, which rises 11 kilometers above the mean planetary radius. These highland regions are thought to be the result of tectonic processes, though Venus lacks the plate tectonics that shape Earth's surface. Venus's lack of plate tectonics is one of the fundamental differences between our neighboring planet and Earth. Instead of the continuous recycling of crustal material that occurs on Earth, Venus appears to undergo periods of relative geological calm, punctuated by episodes of intense volcanic activity that can resurface large portions of the planet. This episodic geological activity may be related to the planet's internal heat budget and the way thermal energy is transported from the interior to the surface. The atmospheric dynamics of Venus create some of the most extreme weather patterns in our solar system. The planet's upper atmosphere is dominated by high speed winds that circle the planet in just 4 Earth days, creating a phenomenon known as superrotation. These winds, which can reach speeds of up to 360 kilometers per hour, are driven by the absorption of solar energy in the upper atmosphere and the efficient heat transport from the day side to the night side of the planet. Lightning on Venus occurs primarily in the planet's lower atmosphere and appears to be associated with volcanic activity rather than the water based thunderstorms we experience on Earth. The lightning is generated by the electrification of ash, particles, and volcanic plumes, creating electrical discharges that illuminate the planet's dense atmosphere. These lightning storms provide valuable information about ongoing volcanic activity on Venus's surface. The study of Venus has profound implications for our understanding of planetary climate and atmospheric evolution. Scientists believe that Venus may have once possessed liquid water oceans, similar to those on early Earth. However, the planet's proximity to the Sun and the gradual brightening of our star over billions of years may have triggered a runaway greenhouse effect that boiled away Venus's oceans and transformed it into the hellish world we observe today. This transformation from a potentially habitable world to an extreme greenhouse planet serves as a cautionary tale about the delicate balance of factors that maintain Earth's climate. The study of Venus helps scientists understand the processes that could affect Earth's climate in the future and provides insights into the range of possible evolutionary paths for terrestrial planets. The exploration of Venus has been achieved primarily through robotic spacecraft, as the planet's extreme surface conditions make it one of the most challenging environments in the solar system for mechanical systems. The Soviet Venera program successfully landed several spacecraft on Venus's surface, providing the first and only images from the planet's surface. These missions revealed a landscape of flat, rocky plains strewn with volcanic rocks, all bathed in the orange glow of sunlight filtered through the dense atmosphere. Venus's gravitational influence on other objects in the solar system has been utilized by spacecraft navigators to provide gravitational assists for missions to the outer planets. The planet's nearly circular orbit and its position in the inner solar system make it an ideal target for gravity assist maneuvers, allowing spacecraft to gain speed and change direction without expending additional fuel. The planet's phases, as observed from Earth, provided some of the crucial evidence for the heliocentric model of the solar system. Galileo's observations of Venus's phases through his telescope showed that the planet must orbit the Sun rather than Earth, supporting Copernicus's revolutionary idea that the Sun, not Earth, is at the center of our solar system. Despite its hostile environment, Venus continues to intrigue scientists and astronomers. Recent discoveries of phosphine in Venus's atmosphere have sparked renewed interest in the possibility of life existing in the planet's upper atmosphere. where temperatures and pressures are more moderate than at the surface. While the existence of life on Venus remains highly speculative, these discoveries remind us that even the most extreme environments may hold surprises. The beauty of the Venus, as seen from Earth, shining brilliantly in our morning or evening sky, contrasts sharply with the harsh realities of its surface conditions. This dichotomy between appearance and reality serves as a reminder that the universe is full of mysteries waiting to be explored and understood. Venus challenges us to look beyond surface appearances and to appreciate the complex processes that shape planetary worlds. As we contemplate Venus in the quiet moments before sleep, we can appreciate this veiled world's contribution to our understanding of planetary science and climate dynamics. The planet serves as both a cautionary example of extreme greenhouse conditions and a testament to the diverse range of environments that exist within our solar system. In its slow, backward rotation and its brilliant presence in our sky, Venus reminds us of the wonderful complexity and variety of worlds that surround us in space. In the vast emptiness of space, approximately 150 million kilometers from our Sun, orbits a small blue world that has become the stage for one of the universe's most remarkable experiments, the development of life. Earth, our home planet, occupies a unique position in our solar system and perhaps in the universe itself. As we pause to contemplate our world from a cosmic perspective, we can begin to appreciate the countless factors that have combined to make our planet not just habitable, but a thriving oasis of life in the apparent desert of space. From the perspective of space, Earth appears as a magnificent blue marble suspended against the black backdrop of the cosmos. This blue color, so distinctive and beautiful, comes from our planet's most precious resource, liquid water. Earth is the only known planet in our solar system where water exists in all three phases: solid, liquid, and gas, simultaneously on its surface. This water, covering approximately 71% of Earth's surface, has been crucial to the development and maintenance of life as we know it. Earth's atmosphere, a thin shell of gases held close to the planet by gravity, creates the protective environment that allows life to flourish. Composed primarily of nitrogen and oxygen, with small amounts of argon, carbon dioxide, and other trace gases, our atmosphere serves multiple vital functions. It protects us from harmful solar radiation, maintains surface temperatures within a range suitable for liquid water, and provides the chemical ingredients necessary for biological processes. The oxygen in our atmosphere, which makes up about 21% of the total, is itself a product of life. For most of Earth's history, the atmosphere contained very little oxygen. It was only after the evolution of photosynthetic organisms, particularly cyanobacteria, that oxygen began to accumulate in significant quantities. This transformation, known as the Great Oxidation Event, occurred approximately 2.4 billion years ago and fundamentally changed the chemistry of Earth's surface and atmosphere. Earth's magnetic field, generated by the movement of molten iron in the planet's outer core, extends far into space and serves as an invisible shield, protecting our world from the solar wind and cosmic radiation. This magnetic field, called the magnetosphere, deflects most of the charged particles streaming from the sun, preventing them from stripping away our atmosphere and bombarding the surface with harmful radiation. The interaction between the solar, wind, and Earth's magnetosphere creates the beautiful auroras that dance across our polar skies. The planet's geology tells a story of constant change and renewal spanning over 4.5 billion years. Unlike the static surfaces of Mercury or Mars, Earth's surface is continuously reshaped by the process of plate tectonics. The planet's outer shell, or lithosphere, is divided into large plates that move slowly across the surface, creating mountains, ocean basins, and volcanic activity. This geological activity has played a crucial role in regulating Earth's climate and maintaining conditions suitable for life. Earth's water cycle represents one of the most elegant and important systems operating on our planet. Solar energy evaporates water from the oceans, rivers, and lakes, lifting moisture into the atmosphere, where it condenses into clouds and eventually falls as precipitation. This continuous cycle of evaporation, condensation, and precipitation distributes fresh water across the continents, moderates temperatures, and supports all terrestrial life. The water cycle also plays a crucial role in the carbon cycle, helping to regulate the amount of carbon dioxide in the atmosphere. The diversity of life on Earth is truly extraordinary, from the deepest ocean trenches to the highest mountain peaks, from scorching deserts to frozen polar regions. Life has found ways to adapt and thrive in almost every environment our planet offers. This biological diversity, or biodiversity, represents billions of years of evolution, during which countless species have developed unique adaptations to their environments. Earth's position in what astronomers call the habitable zone, or Goldilocks zone, around the sun is crucial to our planet's ability to support life. This zone represents the range of distances from a star where liquid water can exist on a planet's surface, too close to the sun, and water would boil away into space, too far away, and water would freeze solid. Earth's orbit places it in the optimal position to maintain liquid water, though this alone is not sufficient to guarantee habitability. The presence of our moon has had a profound influence on Earth's development and the evolution of life. The moon's gravitational pull creates tides in our oceans, which may have played a role in the transition of life from sea to land. The moon also helps stabilize Earth's axial tilt, preventing extreme climate variations that might otherwise make our planet uninhabitable. The moon's influence on Earth's rotation has gradually slowed our planet's spin, lengthening our days from the much shorter days that existed in Earth's early history. Earth's carbon cycle is a complex system that regulates the planet's climate over geological timescales. Carbon dioxide is removed from the atmosphere through weathering of rocks and the burial of organic matter, while volcanic activity and other processes return carbon dioxide to the atmosphere. This natural thermostat has helped maintain Earth's surface temperature within a range suitable for life, despite the gradual brightening of the sun over billions of years. The evolution of photosynthesis represents one of the most important developments in Earth's history. This process, by which plants and other organisms convert sunlight, carbon dioxide, and water into chemical energy, not only provides the foundation for most food webs, but also maintains the oxygen content of our atmosphere. The oxygen we breathe is a direct product of photosynthetic activity, making us dependent on the plant kingdom for our very survival. Earth's seasons result from the planet's axial tilt of approximately 23.5 degrees. As Earth orbits the Sun, different parts of the planet receive varying amounts of direct sunlight throughout the year, creating the seasonal patterns that have influenced the evolution of life and human civilization. These seasonal changes have driven many of the migration patterns, breeding cycles, and other behaviors we observe in the natural world. The development of human civilization has had an increasingly significant impact on Earth's systems. In recent centuries, human activities have begun to influence global climate patterns, atmospheric composition, and biodiversity. Understanding our planet's natural systems and our impact on them has become crucial for ensuring the continued habitability of our world for future generations. From space, Earth's most striking feature is its apparent isolation. Our planet appears as a small, isolated oasis of life in the vast darkness of space. This perspective, first gained by astronauts and dramatically illustrated by photographs such as the famous blue marble image, has profoundly influenced how we think about our place in the universe and our responsibility to care for our home planet. The study of Earth from space has revolutionized our understanding of our planet's systems and their interconnections. Satellite observations allow us to monitor weather patterns, track changes in ice coverage, observe volcanic eruptions, and study the health of forests and oceans on a global scale. These observations have revealed Earth as a single, integrated system where changes in one region can affect conditions around the world. Earth's atmosphere extends much higher than most people realize, gradually thinning until it merges with the vacuum of space. The troposphere, where weather occurs, extends only about 10–15 kilometers above the surface. Above this lies the stratosphere, where the ozone layer protects us from harmful ultraviolet radiation. Higher still are the mesosphere, thermosphere, and exosphere, each with its own unique characteristics and role in protecting our planet. The northern and southern lights, or auroras, provide visible evidence of the continuous interaction between Earth and space. These spectacular displays occur when charged particles from the solar wind interact with our planet's magnetic field and atmosphere, creating curtains of light that dance across the polar skies. Auroras serve as a beautiful reminder of the dynamic nature of the space environment and the protective role of Earth's magnetic field. As we contemplate our home planet from this cosmic perspective, we can appreciate the remarkable series of conditions and events that have made Earth a suitable home for life. From the planet's optimal distance from the Sun to the presence of our large moon, from the development of plate tectonics to the evolution of photosynthesis, countless factors have combined to create the world we know today. This perspective invites us to consider our place in the universe and our responsibility as stewards of this precious blue world that continues to spin peacefully through space, carrying all of life's hopes and dreams with it on its eternal journey around the Sun. Beyond Earth's orbit, in the cooler regions of our solar system, where the Sun's warmth grows gentler and more distant, we encounter Mars, the fourth planet from our central star. This world, painted in shades of rust and amber, has captured human imagination for centuries with its reddish glow in our night sky. Mars represents both a window into our solar system's past and a potential destination for humanity's future, a world that once may have harbored conditions suitable for life and might do so again. Mars orbits the Sun at an average distance of 228 million kilometers, receiving less than half the solar energy that Earth enjoys. This greater distance from the Sun means that sunlight takes approximately 12 and a half minutes to travel from our star to the Martian surface. Despite this reduced solar heating, Mars experiences seasons much like Earth due to its similar axial tilt of about 25 degrees. However, because Mars takes 687 Earth days to complete one orbit around the Sun, each Martian season lasts nearly twice as long as the corresponding season on Earth. The rusty red color that gives Mars its distinctive appearance comes from iron oxide, commonly known as rust, that covers much of the planet's surface. This oxidized iron tells a story of a world that once had a very different atmosphere and climate than what we observe today. The presence of so much oxidized iron suggests that Mars once had liquid water on its surface, and possibly a thicker atmosphere that could support the chemical reactions necessary to create these rust-colored minerals. Mars is significantly smaller than Earth, with a diameter roughly half that of our home planet and a mass only about 11% of Earth's. This smaller size means that Mars has a weaker gravitational field, only 38% as strong as Earth's gravity. A person who weighs 100 kilograms on Earth would weigh only 38 kilograms on Mars. This reduced gravity has important implications for the planet's ability to retain its atmosphere and for any future human exploration of the world. The Martian atmosphere is thin and composed primarily of carbon dioxide, with small amounts of nitrogen and argon. The atmospheric pressure at Mars's surface is less than 1% of Earth's atmospheric pressure, equivalent to the pressure found at an altitude of about 35 kilometers above Earth's surface. This thin atmosphere provides little protection from solar radiation and cosmic rays, and it cannot support liquid water on the surface under current conditions. Despite its current harsh conditions, Mars shows abundant evidence of a more hospitable past. Vast networks of dry riverbeds, ancient lake beds, and what appear to be ocean shorelines tell the story of a world where liquid water once flowed freely across the surface. These features suggest that early Mars had a thicker atmosphere and warmer temperatures that could support stable bodies of liquid water for extended periods. The northern and southern hemispheres of Mars are remarkably different from each other, a phenomenon known as the global dichotomy. The northern hemisphere consists largely of smooth, low-lying plains that may once have been covered by an ocean. The southern hemisphere is heavily cratered and sits several kilometers higher than the northern plains. This dramatic difference between the hemispheres is thought to result from a massive impact early in Mars's history that reshaped the planet's surface. Mars hosts the largest volcano in the solar system, Olympus Mons, which rises about 21 kilometers above the surrounding plains. This enormous shield volcano is roughly the size of the state of Arizona and formed over millions of years as successive lava flows built up the mountain's gently sloping sides. The existence of such large volcanoes on Mars is possible because the planet lacks plate tectonics, allowing volcanic hotspots to remain stationary and build increasingly massive structures over geological time. The planet also features Valles Marineris, a vast canyon system that stretches over 4,000 kilometers across the Martian surface. This canyon system is up to 7 kilometers deep and 200 kilometers wide in some places, making it one of the largest canyons in the solar system. Valles Marineris appears to have formed through a combination of tectonic activity and erosion, possibly including the flow of ancient rivers and floods. Mars experiences dust storms that can cover the entire planet for months at a time. These global dust storms occur roughly every 2 Earth years when Mars is closest to the Sun in its elliptical orbit. The increased solar heating during this period can lift enormous amounts of dust into the atmosphere, creating storms that obscure the planet's surface and can affect the operation of solar-powered spacecraft on the Martian surface. The search for life on Mars has been one of the primary motivations for exploring the planet. While no definitive evidence of life has been found, Mars contains many of the chemical ingredients necessary for life as we know it. The discovery of organic compounds in Martian rocks and evidence of past liquid water has kept alive the possibility that life may have existed on Mars in the past or might still exist in subsurface environments. Mars has two small moons, Phobos and Deimos, named after the Greek gods of fear and panic who accompanied the god of war into battle. These moons are irregularly shaped and quite small, with Phobos measuring about 22 kilometers across and Deimos only about 12 kilometers. Both moons are thought to be captured asteroids, rocky bodies that were gravitationally captured by Mars early in the solar system's history. Phobos orbits Mars at a distance of only 6,000 kilometers above the planet's surface, making it closer to its parent planet than any other moon in the solar system. This close orbit means that Phobos completes 3 orbits around Mars in a single Martian day. The gravitational forces between Mars and Phobos are gradually pulling the moon closer to the planet, and scientists predict that Phobos will either crash into Mars or break apart to form a ring system in about 50 million years. The exploration of Mars has been the subject of numerous robotic missions that have revealed the planet's secrets in increasing detail. Orbital spacecraft have mapped the planet's surface, studied its atmosphere, and monitored its weather patterns. Surface rovers have analyzed Martian rocks and soil, searched for signs of past or present life, and demonstrated technologies that could support future human missions to the planet. Recent discoveries on Mars have included evidence of seasonal methane releases, the presence of liquid water beneath the planet's polar ice caps, and the existence of organic compounds in ancient Martian rocks. These findings continue to fuel speculation about the possibility of life on Mars and have important implications for our understanding of how life might arise and persist on other worlds. The study of Mars provides valuable insights into planetary, climate change, and atmospheric evolution. By understanding how Mars transformed from a world with liquid water and a thicker atmosphere to its current cold, dry state, scientists can better understand the factors that affect planetary habitability and the long term evolution of planetary atmospheres. Mars represents a world of transitions, a planet caught between its watery past and its arid present. The ancient riverbeds and lake beds speak of a time when Mars may have been blue and green like Earth, while its current rusty landscape tells of atmospheric loss and climate change on a planetary scale. This transformation serves as a reminder of the dynamic nature of planetary environments and the delicate balance of factors that determine whether a world can support life. As we contemplate Mars in the quiet darkness of space, we can imagine this russet world slowly rotating on its axis, its polar ice caps gleaming in the distant sunlight, its vast canyons and towering volcanoes, testament to billions of years of geological activity. The planet continues its stately orbit around the sun, carrying with it the secrets of its past and the potential for future discovery. In Mars, we see both a mirror of Earth's possible future and a stepping stone toward humanity's expansion into the solar system. The seasonal changes on Mars, driven by the planet's axial tilt and elliptical orbit, create patterns of atmospheric circulation and surface temperature variation that continue to intrigue scientists. During the Martian winter, carbon dioxide from the atmosphere freezes at the polar caps, lowering atmospheric pressure across the planet. As spring and summer arrive, this frozen carbon dioxide sublimes back into the atmosphere, creating complex patterns of wind and weather that shape the planet's climate. Despite its current harsh conditions, Mars continues to evolve. Geological processes, though much slower than on Earth, continue to shape the planet's surface. Dust storms redistribute surface materials, seasonal changes affect the polar ice caps, and the planet's interaction with the solar wind continues to gradually strip away its thin atmosphere. Mars remains a dynamic world, changing on timescales both human and geological, a reminder that all worlds in our solar system continue their long evolutionary journeys through cosmic time. Beyond the asteroid belt, in the outer reaches of our solar system, where the sun's light grows dim and distant, we encounter Jupiter, the largest and most magnificent of all the planets in our cosmic neighborhood. This gas giant, a world so massive that it contains more than twice the mass of all other planets combined, serves as both a guardian and a guide for the inner solar system. Jupiter's immense gravitational influence has shaped the architecture of our entire solar system, creating a stable environment that has allowed smaller worlds like Earth to develop and thrive. Jupiter orbits the Sun at an average distance of 778 million kilometers, a journey that places it 5 times farther from our star than Earth. At this vast distance, sunlight takes 43 minutes to travel from the Sun to Jupiter, and the solar energy reaching the planet is only 4% of what Earth receives. Despite this reduced solar heating, Jupiter radiates more energy into space than it receives from the Sun, generating internal heat through the slow gravitational compression of its massive bulk. The scale of Jupiter is truly breathtaking, with a diameter of approximately 143,000 kilometers. Jupiter is so large that more than 1,300 Earths could fit within its volume. Yet, despite this enormous size, Jupiter is composed primarily of hydrogen and helium, the lightest elements in the universe. This composition makes Jupiter a failed star of sorts, a world that contains the same basic ingredients as the Sun but lacks sufficient mass to ignite nuclear fusion in its core. Jupiter's atmosphere displays some of the most beautiful and complex weather patterns in the solar system. The planet's rapid rotation, completing one day in just under 10 hours, creates powerful jet streams that organize the atmosphere into distinct bands of clouds. These bands alternate between zones of rising gas, which appear bright and light colored, and belts of descending gas, which appear darker and more reddish in hue. The Great Red Spot, Jupiter's most famous atmospheric feature, is a massive anticyclonic storm that has been raging for at least 400 years, and possibly much longer. This enormous storm is larger than Earth itself, with winds reaching speeds of up to 500 kilometers per hour. The Great Red Spot's distinctive color comes from complex organic compounds created by lightning and solar radiation, acting on the ammonia and other chemicals in Jupiter's atmosphere. Recent observations have revealed that Jupiter's atmosphere extends much deeper than previously thought, with complex circulation patterns that reach thousands of kilometers below the visible cloud tops. The planet's atmospheric dynamics are driven by internal heat as much as by solar energy, creating a weather system unlike anything found on the terrestrial planets. Jupiter's magnetic field is the largest structure in the solar system, extending millions of kilometers into space and trapping charged particles in radiation belts that would be lethal to any spacecraft or human visitors. This magnetic field is generated by the movement of metallic hydrogen in Jupiter's interior, where extreme pressures transform hydrogen into a substance that behaves like a liquid metal. The interaction between Jupiter's magnetic field and the solar wind creates magnificent auroras at the planet's poles, displays of light that dwarf anything seen on Earth. The planet serves as the gravitational center of an entire system of moons and smaller objects. Jupiter's four largest moons, discovered by Galileo in 1610, are worlds in their own right, each with unique characteristics and fascinating histories. Io, the innermost large moon, is the most volcanically active body in the solar system, with sulfur volcanoes creating a constantly changing surface, painted in brilliant yellows and oranges. Europa, the second of the Galilean moons, hides beneath its icy surface a vast ocean that may contain more water than all of Earth's oceans combined. This subsurface ocean, kept liquid by tidal heating from Jupiter's gravity, represents one of the most promising environments for the potential existence of life beyond Earth. The smooth, relatively young surface of Europa suggests that this ocean occasionally breaks through the ice, creating features that hint at the dynamic world hidden beneath. Ganymede, the largest moon in the solar system, is larger than the planet Mercury and possesses its own magnetic field. This remarkable moon shows evidence of past geological activity and may also harbor a subsurface ocean beneath its icy crust. Ganymede's surface displays a complex history of tectonic activity, with dark, ancient terrain interspersed with brighter, younger regions that tell the story of this moon's long evolution. Callisto, the outermost of Jupiter's large moons, is one of the most heavily cratered objects in the solar system. Its ancient, battered surface preserves a record of the early solar system's violent history, when asteroids and comets frequently bombarded the inner planets and moons. Despite its ancient appearance, Callisto may also possess a subsurface ocean, making it another potential harbor for life in the outer solar system. Jupiter's influence extends far beyond its immediate neighborhood. The planet's massive gravity acts as a cosmic vacuum cleaner, capturing comets and asteroids that might otherwise threaten the inner planets. This protective role has been crucial for the development of life on Earth, as Jupiter's gravitational influence has reduced the frequency of major impacts on our planet throughout its history. The planet's gravitational pull also affects the orbits of asteroids in the main belt between Mars and Jupiter, creating gaps known as Kirkwood gaps, where Jupiter's resonant gravitational influence prevents stable orbits. These gaps help maintain the structure of the asteroid belt and influence the long-term evolution of small bodies in the inner solar system. Jupiter's formation played a crucial role in shaping the architecture of our entire solar system. As the first planet to form in the early solar nebula, Jupiter's rapid growth allowed it to capture vast amounts of gas before the young sun's solar wind cleared away the remaining nebular material. This early formation and subsequent migration may have influenced the final orbits of all the other planets, including the positioning of Earth in its current life-supporting orbit. The study of Jupiter has provided insights into the formation and evolution of planetary systems throughout the universe. As astronomers discover thousands of exoplanets orbiting other stars, many of these distant worlds appear to be Jupiter-like gas giants. Understanding our own gas giant helps scientists interpret observations of these distant worlds and understand the role that massive planets play in shaping planetary systems. Jupiter's rapid rotation and massive size create a complex internal structure unlike anything found on the terrestrial planets. At the planet's center lies a core of rock and ice surrounded by layers of liquid, metallic hydrogen, and molecular hydrogen. The transition between these different phases of matter occurs gradually with depth, creating a smooth variation in properties rather than the distinct layers found in rocky planets. The planet's numerous small moons and captured asteroids create a complex gravitational environment that continues to evolve over time. Some of these small moons may be fragments of larger bodies that were broken apart by tidal forces, while others are likely captured asteroids or comets that became trapped in Jupiter's gravitational well. The exploration of Jupiter began with the Pioneer and Voyager spacecraft in the 1970s, which revealed the planet's complex atmosphere and diverse system of moons. More recent missions, including the Galileo orbiter and the ongoing Juno mission, have provided detailed insights into Jupiter's interior structure, atmospheric dynamics, and magnetic field. These missions have revealed Jupiter to be far more complex and dynamic than early telescopic observations suggested. Jupiter's beauty extends beyond its scientific importance. Through even small telescopes, observers can see the planet's cloud bands and track the movements of its largest moons as they orbit the giant world. These observations, accessible to amateur astronomers, provide a direct connection to the discoveries made by Galileo 4 centuries ago and continue to inspire wonder about our place in the cosmos. As we contemplate Jupiter in the vast darkness of space, we can envision this gentle giant slowly rotating in its distant orbit, its great storms swirling through an atmosphere that has remained largely unchanged for billions of years. The planet's family of moons continues their ancient dance around their massive parent, creating a miniature solar system that mirrors the larger cosmic ballet occurring throughout our solar system. Jupiter represents both stability and change in our cosmic neighborhood. While the planet's basic structure and composition have remained constant for billions of years, its atmosphere continues to evolve, its moons continue to change, and its gravitational influence continues to shape the evolution of our entire solar system. In its majestic presence, Jupiter reminds us of the power and beauty of gravitational forces operating on cosmic scales and the remarkable complexity that emerges from the simple attraction between masses in space. In the distant reaches of our solar system, where the sun appears as little more than a bright star in the cosmic darkness, we encounter Saturn, the second largest planet, and perhaps the most visually stunning world in our cosmic neighborhood. Saturn's magnificent ring system, visible even through small telescopes from Earth, has captivated observers for centuries and continues to reveal new wonders as our understanding of this remarkable world deepens. Saturn orbits the Sun at an average distance of 1.4 billion kilometers, nearly twice as far from our star as Jupiter. At this tremendous distance, sunlight takes approximately 80 minutes to travel from the Sun to Saturn, and the solar energy reaching the planet is only about 1% of what Earth receives. Like Jupiter, Saturn radiates more energy into space than it receives from the Sun, generating internal heat through the gravitational compression of its massive bulk. The planet itself is a gas giant composed primarily of hydrogen and helium, with a lower density than any other planet in our solar system. Saturn's density is so low that the entire planet would float if placed in a sufficiently large body of water. This low density results from Saturn's composition and the relatively cool temperatures in the outer solar system, which allow the planet to maintain a large, extended atmosphere. Saturn's atmospheric structure shares many similarities with Jupiter's, featuring bands of clouds organized by powerful jet streams created by the planet's rapid rotation. Saturn completes one rotation in approximately 10 hours and 39 minutes, causing the planet to bulge noticeably at its equator. The planet's atmosphere displays beautiful golden and amber hues, created by ammonia crystals and other compounds in the upper atmosphere. The planet experiences seasonal changes due to its axial tilt of about 27 degrees, similar to Earth's tilt. However, because Saturn takes 29.5 Earth years to complete one orbit around the Sun, each season lasts approximately 7 Earth years. These long seasons create gradual changes in atmospheric patterns and affect the appearance of Saturn's rings as viewed from Earth. Saturn's most famous feature, its ring system, represents one of the most beautiful and complex structures in our solar system. The rings consist of countless particles, ranging in size from tiny grains to house sized boulders, all composed primarily of water ice with small amounts of rocky material. These particles orbit Saturn in an extremely thin disk that extends from about 7,000 kilometers above the planet's surface to more than 80,000 kilometers into space. The main ring system is divided into several distinct regions, labeled with letters in the order of their discovery. The brightest and most massive rings are the A and B rings, separated by the Cassini division, a gap about 4,800 kilometers wide. The fainter C ring lies closer to the planet, while the much fainter D ring extends almost to Saturn's cloud tops. Beyond the main rings lie the tenuous E, F, and G rings, which were discovered by spacecraft missions. The ring particles are organized by complex gravitational interactions with Saturn's many moons. Small moons called shepherd moons orbit just inside and outside some ring sections, using their gravity to keep ring particles confined within narrow bands. Larger moons create gaps in the rings through gravitational resonances, while still other moons contribute material to the rings through impacts or volcanic activity. The origin of Saturn's rings remains one of the great mysteries of planetary science. The rings could be the remnants of a moon that was torn apart by tidal forces or destroyed by an impact, or they might be leftover material from the formation of the Saturn system that never coalesced into a moon. Recent evidence suggests that the rings may be relatively young, perhaps only a few 100 million years old, rather than dating back to the formation of the solar system. Saturn hosts a diverse family of at least 146 known moons, ranging from tiny irregular objects only a few kilometers across to Titan, which is larger than the planet Mercury. This extensive moon system creates a complex gravitational environment that influences the structure and evolution of Saturn's rings, while providing a laboratory for studying the formation and evolution of satellite systems. Titan, Saturn's largest moon, is one of the most fascinating worlds in our solar system. This remarkable moon possesses a thick atmosphere composed primarily of nitrogen, with significant amounts of methane and other organic compounds. Titan's atmosphere is so dense that it exerts a surface pressure 1.5 times greater than Earth's atmosphere, and it supports a complex weather system with clouds, rain, and seasonal changes. The surface of Titan features lakes and rivers of liquid methane and ethane, creating a landscape that resembles Earth's in many ways, but with exotic chemistry. These hydrocarbon lakes and rivers undergo seasonal changes as Titan orbits Saturn, with some bodies of liquid appearing and disappearing over periods of several Earth years. The presence of complex organic chemistry on Titan makes it one of the most promising places to search for life beyond Earth. Enceladus, another of Saturn's moons, has revealed itself to be geologically active despite its small size. This icy moon shoots geysers of water vapor and ice particles from its south polar region, creating the material that forms Saturn's E ring. These geysers suggest that Enceladus harbors a subsurface ocean beneath its icy crust, making it another potential habitat for life in our solar system. The geysers of Enceladus were discovered by the Cassini spacecraft, which spent 13 years studying the Saturn system from 2004 to 2017. Cassini's observations revolutionized our understanding of Saturn and its moons, revealing the complexity of the ring system, the active geology of several moons, and the intricate gravitational interactions that govern the entire system. Saturn's magnetic field, while weaker than Jupiter's, still extends far into space and traps charged particles in radiation belts around the planet. The interaction between Saturn's magnetic field and its ring system creates unique phenomena, including spokes in the rings caused by electrostatic forces and auroras that occur over the planet's polar regions. The planet's hexagonal storm at its north pole represents one of the most unusual atmospheric features in the solar system. This six-sided jet stream, larger than Earth itself, has maintained its shape for decades, demonstrating the long-term stability of atmospheric patterns. On gas giant planets, the hexagon rotates with the same period as Saturn's interior, providing clues about the planet's internal structure and rotation. Saturn's influence on the solar system extends beyond its immediate neighborhood through its gravitational interactions with other planets and small bodies. The planet serves as a source of long-period comets when gravitational perturbations send objects from the outer solar system into the inner regions where they become visible from Earth. The beauty of Saturn has made it a favorite target for amateur astronomers, and even small telescopes can reveal the planet's rings and largest moons. The changing orientation of the rings as Saturn orbits the Sun creates a slowly evolving view that has been observed and documented by astronomers for centuries. Saturn's ring system provides a natural laboratory for studying fundamental physics, including orbital mechanics, particle interactions, and wave phenomena. The rings display features such as density waves and spiral arms that help scientists understand similar structures in other astronomical contexts, including galaxies and protoplanetary disks around young stars. The seasonal changes on Saturn affect both the planet's atmosphere and its ring system. As different parts of the planet receive varying amounts of sunlight throughout Saturn's long year, atmospheric patterns shift and evolve. The rings also undergo seasonal changes, with some features becoming more or less prominent as the ring plane tilts relative to the Sun. Recent discoveries have revealed that Saturn's rings may be much more dynamic than previously thought, with evidence of ongoing processes that create and destroy ring material over relatively short timescales. This dynamism suggests that Saturn's rings may have looked quite different in the past and will continue to evolve in the future. As we contemplate Saturn in the quiet depths of space, we can envision this magnificent world slowly rotating within its ethereal ring system, its many moons orbiting in complex patterns around their golden parent planet. The entire system exists in a delicate gravitational balance that has persisted for millions or billions of years, creating one of the most beautiful and harmonious structures in our solar system. Saturn represents the power of gravity to create order and beauty on cosmic scales. The planet's rings, despite being composed of countless individual particles, move in perfect accordance with the laws of orbital mechanics, creating patterns and structures of breathtaking elegance. In its serene journey around the Sun, Saturn reminds us that even in the vast emptiness of space, natural forces can create phenomena of extraordinary beauty and complexity. As we venture beyond Saturn's ethereal realm, we enter the most distant and mysterious regions of our solar system, where the sun's warmth becomes a distant memory and the darkness of interstellar space begins to assert its presence. Here, in these remote corners of our cosmic neighborhood, we encounter worlds of ice and mystery, objects that challenge our understanding of planetary formation and reveal the incredible diversity of environments that exist within our solar system. Uranus, the seventh planet from the Sun, orbits at an average distance of 2.9 billion kilometers from our star. At this tremendous distance, sunlight takes 2 hours and 40 minutes to reach Uranus, and the solar energy received by the planet is only about 0.25% of what Earth receives. This ice giant world, composed primarily of water, methane, and ammonia ices surrounding a rocky core, represents a fundamentally different type of planet from the gas giants Jupiter and Saturn. The most remarkable characteristic of Uranus is its extreme axial tilt of 98 degrees, which means the planet essentially rolls along its orbital path rather than spinning upright like most other planets. This unusual orientation causes Uranus to experience the most extreme seasonal variations in the solar system, with each pole experiencing 42 years of continuous sunlight, followed by 42 years of continuous darkness during the planet's 84-year orbital period. Uranus appears as a serene, blue-green world when viewed through telescopes, its color resulting from methane in the planet's atmosphere, which absorbs red light and reflects blue and green wavelengths back into space. The planet's atmosphere is composed primarily of hydrogen and helium, with approximately 2% methane and traces of other compounds. Despite its distance from the Sun, Uranus experiences winds that can reach speeds of up to 900 kilometers per hour. The planet possesses a complex ring system, though much fainter and narrower than Saturn's magnificent rings. Uranus's rings were discovered in 1977 and consist of dark particles, possibly organic compounds altered by radiation. These rings are kept in place by small shepherd moons and demonstrate that ring systems can exist around planets throughout the solar system, not just around the gas giants. Uranus hosts 27 known moons, named after characters from the works of William Shakespeare and Alexander Pope. The largest of these moons, Miranda, Ariel, Umbriel, Titania, and Oberon, display a fascinating variety of geological features that speak to complex histories of formation and evolution. Miranda, in particular, shows evidence of intense geological activity in its past, with a surface that appears to have been broken apart and reassembled multiple times. Beyond Uranus lies Neptune, the outermost of the traditional planets and the windiest world in our solar system, located an average of 4.5 billion kilometers from the Sun. Neptune receives less than 0.1% of the solar energy that reaches Earth. Sunlight takes over 4 hours to travel from the sun to this distant world. Yet Neptune somehow generates enough internal heat to drive the most powerful winds in the solar system. Neptune's deep blue color comes from methane in its atmosphere, which absorbs red light even more efficiently than the methane in Uranus's atmosphere. The planet experiences winds that can exceed 2,000 kilometers per hour, moving in the direction opposite to the planet's rotation. These supersonic winds remain one of the great mysteries of planetary science, as it's unclear how a world so far from the sun can generate such tremendous atmospheric energy. The planet's most famous atmospheric feature was the Great Dark Spot, a massive storm system comparable in size to Jupiter's Great Red Spot. However, when the Hubble Space Telescope observed Neptune years after Voyager 2's flyby, the Great Dark Spot had disappeared, suggesting that Neptune's atmospheric features are much more dynamic and short lived than those on Jupiter. Neptune possesses a complex magnetic field, tilted 47 degrees from its rotational axis and offset from the planet's center. This unusual magnetic field configuration, similar to that found at Uranus, suggests that the magnetic fields of ice giant planets are generated in their mantles rather than in their cores, providing insights into the internal structure of these distant worlds. Triton, Neptune's largest moon, is one of the most intriguing objects in the solar system. This moon orbits Neptune in a retrograde direction, opposite to the planet's rotation, suggesting that Triton was once a captured Kuiper Belt object. Despite its great distance from the Sun, Triton shows evidence of geological activity, including nitrogen geysers that erupt from its surface and create dark streaks across its icy landscape. Beyond Neptune lies the Kuiper Belt, a vast region of space populated by countless icy objects left over from the formation of the solar system. These Kuiper Belt objects, or KBOs, range in size from small comets to dwarf planets and represent pristine samples of the material from which the outer planets formed. The Kuiper Belt extends from about Neptune's orbit to approximately 50 astronomical units from the Sun, creating a reservoir of comets and other small bodies. Pluto, once considered the ninth planet, resides in the Kuiper Belt as the most famous of the dwarf planets. This small, icy world, along with its large moon Charon, represents a double planet system where both objects orbit around a point between them. Pluto's highly elliptical orbit sometimes brings it closer to the Sun than Neptune, though gravitational resonances ensure that the two objects never collide. The exploration of these outer worlds has been challenging due to their vast distances from Earth. The Voyager 2 spacecraft remains the only human-made object to visit Uranus and Neptune, providing our most detailed observations of these distant ice giants. The New Horizons mission's flyby of Pluto in 2015 revealed a world far more complex and geologically active than anyone expected, with evidence of recent geological activity and a thin atmosphere. Beyond the Kuiper Belt lies the scattered disk, a region of space populated by objects with highly elliptical orbits that may represent the transition zone between the Kuiper Belt and the Oort cloud. The Oort cloud, a theoretical sphere of icy objects surrounding our solar system at distances up to 100,000 astronomical units from the Sun, represents the outermost boundary of our solar system's gravitational influence. These distant regions of our solar system are subject to the gravitational influence of nearby stars, which can occasionally perturb the orbits of Oort cloud objects and send them falling toward the inner solar system as long period comets. These visitors from the outer darkness carry with them information about the conditions and composition of the early solar system, preserved in their icy nuclei for billions of years. The study of the outer solar system has revealed the incredible diversity of environments that exist within our cosmic neighborhood, from the methane lakes of Titan to the nitrogen geysers of Triton, from the diamond rain that may fall in the atmospheres of Uranus and Neptune to the complex organic chemistry occurring in the outer reaches of our solar system. These distant worlds continue to surprise and challenge our understanding of planetary science. The heliopause, the boundary where the solar wind meets the interstellar medium, marks the edge of our solar system's sphere of influence. The Voyager spacecraft have crossed this boundary and entered interstellar space, providing our first direct measurements of the environment beyond our solar system. Even in this distant realm, the influence of our Sun continues to be felt, though it gradually gives way to the cosmic environment of our local galactic neighborhood. As we consider these distant realms of our solar system, we are reminded of the vast scales of space and time that govern cosmic evolution. The outer planets and their moons formed billions of years ago from the same material that created our Sun and inner planets, yet their great distance from our star has preserved conditions and processes that provide windows into the early history of our solar system. The continuing exploration of these distant worlds promises to reveal new insights about the formation and evolution of planetary systems, the potential for life in extreme environments, and the processes that govern the long term stability of our cosmic neighborhood. Each new discovery in the outer solar system adds to our understanding of the remarkable diversity and complexity of the worlds that share our journey around the Sun. In the quiet darkness of these distant realms, where the Sun appears as nothing more than a bright star among many others, we find worlds that continue their ancient dance around our central star, carrying within them the secrets of our solar system's birth and the promise of future discoveries. These distant guardians of our cosmic neighborhood remind us that our solar system extends far beyond the familiar worlds of the inner planets, reaching into the darkness of space where ice and mystery reign supreme. As we conclude our journey through our solar system, from the Sun's brilliant nuclear furnace to the icy darkness of the Kuiper Belt and beyond, we can appreciate the remarkable variety and beauty of the worlds that make up our cosmic neighborhood. Each planet, moon, and small body tells its own unique story of formation, evolution, and endurance, contributing to the greater narrative of our solar system's magnificent complexity. The gentle rhythms of celestial mechanics continue their eternal dance, each world following its appointed path through space with the precision of a cosmic clockwork. From Mercury's swift 88-day orbit to Neptune's stately 165-year journey around the Sun, Each planet maintains its place in the grand symphony of gravitational forces that binds our solar system together. In this vast cosmic theater, we find ourselves as both observers and participants, riding aboard our blue marble as it spins through space at tremendous velocities that we cannot feel. Earth carries us at 30 kilometers per second around the sun, while our entire solar system travels at 220 kilometers per second around the center of our galaxy. Yet, despite these incredible speeds, we experience only the gentle passage of days and nights, seasons and years, as our planet maintains its steady course through the cosmos. The forces that shaped our solar system billions of years ago continue to operate today, though on timescales that dwarf human experience. Gravitational interactions slowly modify planetary orbits. Tidal forces gradually slow rotations, and the patient work of stellar evolution continues in our sun's core. These processes remind us that our solar system is not a static collection of worlds, but a dynamic, evolving system that will continue to change over billions of years to come. As we settle into peaceful contemplation of our cosmic home, we can take comfort in the stability and reliability of the celestial cycles that govern our world. The sun will rise tomorrow, as it has for billions of years. The moon will continue its monthly dance around Earth, and the planets will maintain their ancient orbits around our central star. In this cosmic regularity, we find a profound sense of order and continuity that connects us to the deepest rhythms of the universe itself. The story of our solar system is ultimately a story of transformation and possibility. From the primordial nebula that gave birth to our sun and planets to the complex worlds we observe today, our cosmic neighborhood demonstrates the universe's capacity to create beauty, complexity, and perhaps even life from simple beginnings. In understanding our solar system, we gain perspective on our place in the cosmos and appreciation for the remarkable journey that has brought us to this moment in space and time. As the gentle void of space surrounds our solar system, cradling it in the vast darkness between the stars, we can rest assured that we are part of something much larger than ourselves. Our solar system, our galaxy, and the universe itself continue their ancient dance of evolution and change, carrying us forward into a future filled with wonder and possibility. In this knowledge, we find peace, belonging, and the profound comfort that comes from understanding our true home among the stars. The cosmic lullaby of orbital mechanics continues its gentle song as worlds spin and orbit in perfect harmony, each following the gravitational melodies that have guided them for eons. As we prepare for rest, we can imagine ourselves floating peacefully in space, surrounded by the serene beauty of our solar system, feeling the gentle pull of gravity that connects all things and the quiet confidence that comes from being part of this magnificent cosmic family. In the silence of space, where no sound can travel, but where the music of the spheres plays on through gravitational harmonies, we find the perfect environment for peaceful contemplation and restful sleep. Our solar system continues its journey through the galaxy, carrying with it all the hopes and dreams of life on Earth, moving through space with the patience and grace of cosmic time itself. Let the knowledge of our place in this vast and beautiful solar system bring comfort and perspective as consciousness gently fades into the peaceful realm of dreams. We are children of the stars, inhabitants of a remarkable cosmic oasis, participants in an ongoing story of evolution and discovery that stretches across billions of years and countless worlds. In this understanding, we find both humility and wonder, both connection and peace, as we settle into the eternal rhythms of the cosmos and allow ourselves to be carried gently into the restorative embrace of sleep. The solar system continues its ancient dance around the sun, each world maintaining its appointed course through space with the reliability and grace that has characterized celestial motion since the beginning of time. In this cosmic symphony, we find our place, our purpose, and our peace, surrounded by the infinite beauty and complexity of the universe we call home.